Thank you to Brilliant for supporting PBS. If we discover how to connect quantum mechanics with general relativity, we'd pretty much win physics. There are multiple theories that claim to do this, but it's notoriously difficult to test them. They seem to require absurd experiments like particle colliders the size of galaxies. Or we could try to physics smarter instead of physicsing harder. Let's talk about some of the ideas for quantum gravity experiments that can be done on a non-galaxy-sized lab bench, and in some cases already have been done. It's been almost exactly 100 years since quantum mechanics was discovered, and 110 since general relativity. Together these theories explain almost everything. Quantum gives us the behaviour of the subatomic world, and so the building blocks of all matter and their interactions via the quantum forces, and GR gives us the background in which that matter lives, space and time along with the force of gravity. Despite their incredible successes in their own domains, the two theories seem to contradict each other in deep ways. Now, there must be some master theory that encapsulates both and resolves these contradictions. But in the century following the discovery of general relativity and quantum mechanics, our efforts to find that theory have come up short. The common approach to reconciling general relativity with quantum mechanics has been to quantize gravity, to make the gravitational field and so the geometry of space-time obey the strange rules of quantum mechanics. And why not? It's worked for everything else. For example, we made the electromagnetic field quantum, showing that it was mediated by force-carrying photons. And that was a stunning success. But quantizing gravity proved extraordinarily difficult. The hypothetical force carrier for gravity, the graviton, has an energy so tiny that it's hard to even conceive of an experiment that would detect it directly. And then there's the fact that the field of gravity is the fabric of space-time itself. We quantize the other forces of nature with respect to a continuous background of space and time. But so far it's been exceptionally challenging to quantize that background itself. The most prominent approaches like string theory and loop quantum gravity may have made progress, but they struggle to make testable predictions. So what if we've been looking at it the wrong way around? What if instead of quantizing gravity we should be trying to gravitize the quantum? That is, instead of trying to give quantum properties to gravity, we should accept that gravity is fundamentally classical and try to understand how truly quantum matter can result in truly classical gravity. Now, we talked about approaches in which gravity stays classical in the last episode, when we explored the new post-quantum gravity hypothesis of Jonathan Oppenheim, in which random fluctuations in the gravitational field act on the quantum wave function, causing it to collapse. We also talked about the Diosy-Penrose model a while ago, in which a superposition of different spatial distributions of mass and energy is ultimately forced to choose one such distribution consistent with a singular gravitational field. There are compelling reasons on both sides of the discussion, but which is it? Is gravity quantized or is the quantum gravitized? Unlike many questions about quantum gravity, this one may be possible to answer with actual doable experiments. Let's consider the two scenarios and see which predictions they make that we might be able to test. 1. Gravity is quantum. This means gravity, and by extension the fabric of space-time, exhibit the various weird properties of the quantum world like superposition and entanglement. If we can experimentally demonstrate one of these things, then we know gravity is quantum. 2. The quantum is gravitized. This can be tested in the context of specific scenarios like the Diosy-Penrose model or Oppenheimer's post-quantum gravity. Now, I'm going to talk about gravitizing the quantum first, but then I'll come back to tests of actual quantum gravity. In both the Diosy-Penrose and Oppenheim approaches, the gravitational field is responsible for collapsing the quantum wave function. In these ideas, there's only one gravitational field, only one space-time, and quantum systems do quantum stuff within that classical background. One of the things quantum systems can do is to be in superpositions of states. They can exist simultaneously in multiple states at once, like Schrödinger's alive and dead cat. The job of the quantum wave function is to describe this range of possible states. Measurement or observation collapses the wave function. It forces the system to choose one state from the possibilities. If gravity is classical, then the superposition of its contents shouldn't cause a superposition of the gravitational field. A superposition might involve different distributions of mass, which normally would mean different spacetime curvatures, perhaps a superposition of spacetimes. But if gravity is classical, then there's only one spacetime regardless of its contents. This could lead to a tension between the gravitational field and the matter producing that field. The Diosy-Penrose approach says that when the tension gets too large, the wave function collapses. Another way to think about it is that the fuzziness in the matter distribution is within a certain range of matching a single spacetime curvature, and in that case it can stay in superposition. But if that distribution of matter strays outside that range, then its superposition collapses into a well-defined matter distribution. Oppenheim's post-quantum gravity is slightly different. It states that the gravitational field contains random fluctuations, called gravitational diffusion, that mess up quantum superpositions, causing them to collapse. Both the Oppenheim and the Diosy and Penrose approaches make a similar prediction, that there should be a stochastic quality to the gravitational force or its effect. This gravitational diffusion might be the most straightforward thing to test, if it exists. It would imply that there's a fundamental limit to the precision with which any mass can be measured. So, if we can build a set of scales with a certain very high precision, then if the weights it measures appear to fluctuate outside that precision, it may suggest an intrinsic uncertainty in the gravitational field. The most accurate experiment measuring an object's mass conducted so far has led researchers to rule out versions of the theory with rapid spacetime diffusion, implying that any gravity-induced collapse from this mechanism is very weak. Oppenheim and team propose other tabletop experiments that could constrain this better in the future. Rather than look for the funky behavior of the gravitational field, we can also approach this from the other side, by trying to see when the collapse of the wave function happens. If we can see where quantum superposition gives way to classical matter, we may be able to figure out whether it's gravity causing that collapse. Both the Oppenheim and Diosy-Penrose models, as well as any of the family of models known as objective collapse theories, predict that wave function collapse becomes increasingly likely as the object grows in size or mass. If any of these ideas are correct, then there should be a limit to how large an object we can put into superposition for any appreciable amount of time. So far, we've not found such a hard limit, and we've been able to put some pretty big things in superposition. For example, getting interference patterns from large molecules in the double-slit experiment. Based on the larger systems that have been put into superposition, we can rule out theories where gravity-induced collapse is very strong. So, we have some constraints on these ideas where a classical-ish gravity is influencing the quantum wave function of matter. And more advanced tests are being planned that may turn up something. Of course, it may be that gravity really isn't classical in the way that these theories propose. It may be that gravity really is quite quantum, just like matter. If that's the case, then we need different experiments. Two of the strangest properties of quantum objects are superposition, which we just talked a lot about, and entanglement. Quantum entanglement is when you have two quantum systems that each may be in a superposition of states, but the systems are also correlated so that the state of one depends on the state of the other. For example, a quantum coin could be in a superposition of both heads and tails, and a pair of quantum coins could be both in superposition but also be entangled, so they would be, for example, in the opposite state to each other. Even though each of the coins is fundamentally undefined in its state, if the first coin is measured so that its wave function collapses to either heads or tails, its entangled partner's wave function will immediately collapse to the opposite. Quantum entanglement sounds like an exotic phenomenon, but it's not. Quantum particles are constantly getting entangled with each other. In fact, every interaction between particles generates entanglement, even if that entanglement doesn't last very long. We've observed these entanglements when the interaction happens via quantum forces, for example, when particles interact by exchanging the photons of the electromagnetic force. So what if we could cause particles to become entangled by a gravitational interaction? As I'll try to convince you, this would mean that the gravitational field itself has to be part of the entanglement of those objects, and space-time has to be in a superposition of states, which would mean that space-time has to be quantum. One particular proposal for this type of experiment was recently put forward. It's known as quantum gravity-induced entanglement of masses, QGEM. I'll describe the original version proposed by Sugatu Bose and collaborators in 2017. It uses a Stern-Gerlach interferometer. This is the device that first demonstrated the existence of quantum spin back in the 20s. The original version used silver atoms, which have a single unpaired electron in their outer shell, so the atom takes on the quantum spin of that lone electron. That gives the atom a tiny dipole magnetic field. This causes the atom to be deflected when it passes through the external magnetic field of the Stern-Gerlach device. It's deflected upwards if its spin axis is pointed up, and downwards if its spin is down. Because quantum spin is quantum, all atoms will be measured to have either spin fully up or spin fully down, deflected all the way up or deflected all the way down. There are no in-betweens for quantum properties like this. If the atom starts in a superposition state of being both spin up and spin down, then it'll end up in a superposition state of being physically up or down just before it hits the detector screen. So we've turned a spin superposition into a spatial superposition. At the screen, the superposition collapses into one or the other location. But we can also remove the screen and use more magnets to bring the spatial superpositions back together, in which case we turn the spatial superposition back into a spin superposition. Now if we measure that spin, we should find that it collapses completely randomly into 50-50 spin up or spin down. Now, if we were to run a second Stern-Gerlach interferometer next to the first, the spins we'd measured at the end of the second device would have no relationship to the spins measured at the end of the first. Atoms in the different devices are uncorrelated because they're not entangled. But now, let's move the devices really close together. The spin up path of interferometer 1 is right alongside the spin down path of interferometer 2. Let's pretend for a moment that the silver atoms can interact gravitationally. The spin up 1 and spin down 2 atoms tug on each other ever so slightly, while the other paths are too far for the atoms to interact. Remember that the spin measurements at the output of the interferometer 1 versus interferometer 2 used to be random, uncorrelated. Up, down, up, down, up should all be equally likely results of measuring those final spins. Any quantum interaction, though, should generate entanglement between these. So now, if gravity is quantum, the outputs of the two interferometers will be entangled and will be correlated. For example, depending on how this is set up, you might find that the interferometers produce opposite spin results to each other very slightly more often than the same spin results. Now, single atoms are way too light to produce a measurable entanglement. But what if we could do this with many atoms? Specifically with a nanodiamond. These are tiny diamonds with widths measured in nanometers. A little defect inside the diamond crystal structure can be created by removing one carbon atom and replacing it with a neighbouring nitrogen atom. This leaves an unpaired electron, which gives the nanodiamond a net spin. The same technology is actually a candidate for qubit storage in quantum computers. So we create nanodiamonds and put their unpaired electrons in a spin superposition, then shoot them through the pair of Stern-Gerlach devices. In principle, we should get a spatial superposition of these relatively massive crystals, And if gravity is quantum, we should get entanglement between the devices that will be reflected in correlations in their final spins. What would all of this mean if it proved to work? Well, from the point of view of particle physics, the masses get entangled when gravitons are exchanged between the two masses. This is just like in electromagnetism, where photon exchange leads to the electromagnetic force, and sometimes to entanglement. We've made a video before on how hard it is to detect single gravitons, even in principle, so this entanglement between the two masses in the QGEM experiment might be considered indirect evidence for the existence of gravitons, the hypothetical quantum carrier of gravity. From the point of view of general relativity, the superposition of gravitational forces could be interpreted as a superposition of space-time geometries. So space-time itself would be exhibiting one of the most quantum of all properties. In general, a positive QGEM result would be strong evidence that gravity is indeed quantum. These are just some of the experiments that have been proposed, or in some cases actually conducted, to test some of these ideas about the link between quantum mechanics and gravity. Whether to find quantum effects in the gravitational field, or to show that gravity doesn't even need to be truly quantum. There are lots of other ideas and efforts in progress beyond these, and there's a good chance that some will bear fruit, perhaps finally unlocking that century-old mystery of the quantum nature of space-time. Thank you to Brilliant for supporting PBS. Brilliant is where you learn by doing, with thousands of interactive lessons in physics, math, programming, and AI. Brilliant helps you build your critical thinking skills through problem solving, not memorizing. Each lesson is filled with hands-on problem solving that lets you actually play with concepts. And if you're fascinated by AI, How LLMs Work is an immersive AI workshop that lets you experience and harness the mechanics of today's most advanced tools. You'll get hands-on experience with real language models as you explore how they build vocabulary, choose the next word, and more. You'll understand the importance of training data by comparing models trained on pop lyrics to models trained on a cookbook or big text terms and conditions. Finally, you'll learn how to tune an LLM to generate different kinds of output, whether it's poetry or a cover letter. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/spacetime or click on the link in the description. If you go now, you'll also get 20% off an annual premium subscription.